in the manuscript I pulled out from the web. And from the y's, I calculate back the original variables, which are actually the z's. So these are my 3 compressibility factor solutions. And each one of them is translated into a molar volume. Okay, using the definition of the compressibility, the relation between compressibility factor and molar volume. Lower T is the temperature, P is pressure, gas constant. Okay, these are it's a very straightforward problem. And then here's the output for graph and for the tables. So I only output if the molar volume is positive. Remember, it could happen that you have at some solution, it could be that this solution happens on negative. Mathematically, you have 3 solutions, but it could happen also that you have a situation where it looks like that. In this case, obviously, a negative molar volume makes no sense. In this case, you only have one solution because the other one would have been negative. So that would be another case with the only one. So I'll only care if V1 is positive. So how do I calculate things? H1 is calculated, is the function for the departure enthalpy that we calculated. Okay? H1 is the first, which is the ideal that we calculate the moment that we gave temperature at the beginning, plus what we derived was for the Peng-Robinson. Then S is what? S ideal plus what we calculate. S ideal is what? The S ideal temperature part minus R log is ln in VBA, P over the reference, and the reference is what? 1 bar or 100,000 pascals. So this is P over P reference. So this part, S ideal part plus this, is what is S ideal plus the rest. G is calculated as H minus this. Okay? And, okay, the rest two have to do with you guessed. And then here I output the results. Pressure is outputted by dividing by 10 to the 6. So that's in megapascals. Right? Let's see, 10 to the 6 pascals. Yeah. Yeah, pressure is in megapascals. And you can see what I have output. The second solution is the one that is unstable. So for my purpose, I had printed the rest at the beginning, but if you put an apostrophe to the left, that makes it a comment. That's why nothing is printed there, except the only time I want to see the middle one is in the first diagram, pressure, molar volume, I want to see all 3. So that one doesn't have an apostrophe for the molar volume and the pressure. Clear, everyone? And then is the third one, like the first one. If there's one real root, exactly the same thing, follow the equation. And then we change that, and then I increment pressure by a certain step, and look back. It's a very simple program. It has a lot of lines, but it's a very simple program. You see the principles? Sorry, let me just finish this and then we'll ask. You see what I used here? I used departure quantities. I calculate everything from departure quantities, and we already derived in class the equations that are in this program for Peng-Robinson. And calculated first things that are absolute constants. Then we select temperature. Once temperature is selected, I calculate everything that's temperature dependent. I don't want to be calculating those inside the loop, because it should slow it down. Inside the pressure loop, I only calculate things that depend on pressure. So H was calculated outside the loop, and the temperature independent part, the pressure independent part, the temperature dependence for enthalpy, ideal gas entropy was calculated outside. Then the loop calculates the solution first of all for compressibility factor, and it finds 1 or 3. Then from that solution, it calculates entropy, first of all, enthalpy by adding to the ideal gas the equation for Penck-Robinson that we have derived. Same way, it calculates entropy by adding the ideal gas pressure-dependent part to the temperature-dependent part, plus the departure that we have derived in class. Calculates GSH minus TS. And, sorry, your question.
You said the enthalpy in here doesn't account for like the reaction energy?
Yes, yes. So I use a reference enthalpy 0 for anything at 25 degrees C, 1 bar. Yeah. I could modify it to add, but then there would be another input to use. And in terms of any calculation we do in this class, there's no reason we're not going to do any calculation of reactions. And there's no great advantage to not putting a heat of reaction and changing your enthalpy basis. So, any other questions? Okay. So one of the things I expect to be able to do is to modify this problem according to different substances. So if you look at samples of exam of the computer exam, typically I will ask you to use this program for a substance that is not the ethylene that is here. Okay, so you will have to go to Unisim, find the critical values, eccentric, molecular weight, find the parameters of CP star, modify those, and run the code. Any questions?
Do you modify this program here, or just the inputs of the Excel?
Just the Excel, yeah, that's it, yeah. I mean, the one thing that I'm always tempted in doing is assigning you to change the program for SRK, in which you change where I have the Penck-Robinson equations to the equivalent equations for SRK. It will be a very straightforward job. What was that? Happiness?
You always do it for extra credit.
I don't want to enter class 8 minutes early, so let's move on to at least the beginning of your gases. I will again point out to this plot here. Let's go back to what's the plot?
It's down. It was on the. There you go. Yeah, up.
I'll point out again to this plot. You can say that as pressure approaches 0, G ideal gas blows up. That's the motivation behind the concept of fugacity. Let's continue. And there are different alternative definitions of fugacity. And the one that I like the best by far is the one in your text. So 6 minutes, guys. So we know, we know that G ideal gas at any temperature and pressure minus G ideal gas at temperature and another pressure, let's say P naught, is going to be how do we know that? How would I got this? How did I get this? What is partial G with respect to P at constant temperature?
Some dp or something.
You should know this. dG, by the way, those equations should be in everyone's.
Oh.
So, constant temperature, what's that? That's partial G with respect to P at constant temperature, right? Right? And for the ideal gas, so for ideal gas, right? So the integral, this change is the integral of V ideal gas, dp, we just worked with that, right? So it's the integral RT, so let's say from P naught to P. So because temperature is constant, so RT factors out, and you have integral dP over P from P naught to P. In other words, RT ln P over P naught. Okay? What happens as P goes to 0? What happens to ln P over P naught as P goes to 0, no matter what reference you have? Notice the negative infinity. That's what we saw also with the software. So keep that in mind, that this is the relationship between G ideal gas between two different pressures. We'll get an expression for H and S, and I'll use G equals H minus Ts to get the departure G. So if you recall, H minus H ideal gas at any temperature and pressure, the departure one we derive is equal integral T P equals 0 to Tp of V minus T partial V with respect to T at constant T dP. And similarly, we have departure entropy minus integral T equals 0 to Tp of another bracket, which is partial V with respect to T at constant P minus R over V dP. So J, which is H minus Ts, will give us, so J departure is H departure minus Ts departure, and that will give us integral, and I'll stop as soon as I write this. So J departure at any temperature and pressure, you see from here, is integral from T, P equals 0, to T comma P, of things cancel out between the two, and the net result is V molar minus RT over P dV. And this is equation 7, 4, 5p in the text. And this is a good stopping point. And of course, fugacity will be introduced first lecture after algebra. That's exactly what I wanted to be before algebra. Any questions?
The exams that go up to fugacity, like up to.
The exams include what I covered in the program here. So you see, for example, in previous exams, if I can quickly, I will cover that in the review, but if I can quickly show you, let's see what website. We go back and look at previous exams. So if you, I remember 2015, okay, 2015 I may have covered a little bit more than, 2015 was done. Here I may have covered just a little bit more, I may have covered just a little bit about, no, okay. So you can see, actually, you can see it here. You recognize this chart? So now you know that I could very well have a problem like this. In 2015, you can see, I'm giving you the plot. On the plot, identify which line corresponds to the liquid phase, how many phases are in equilibrium at the pressure at which the two lines intersect, what is the pressure at which the two lines intersect called. Not a very difficult problem, but I covered it right before the exam, so, and not for many points, only 10 points. Obviously, you know the answer to that problem now, right? Yes, exactly. Yeah, the pressure oxidation is called Labor's. Yes, sir. Yeah, okay, you can have, a good thing for asking, you can have 4 sheets, no, 4 pages. And a page is a side. So this is a page, the back would be a different page. So you can either have 4 sheets single-sided or 2 sheets double-sided. Yes, as a matter of fact, do bring calculators. You need to calculate things by logs, etc. So you will need a scientific calculator. Or we can do logs. Any other questions regarding the exam? So we'll have review tomorrow, starting at 3:30. Not in this room. I don't know if we have this room, but.